Hi everyone, this is the online lecture on analyzing survey data. So I want to start out with a little bit of a refresher to what we talked about in our last session, which is thinking about the difference between outcomes and drivers and generally thinking about what should you measure within an employee attitude survey. So outcomes are the things that are kind of like the main thing we care about from a motivational standpoint. So engagement, job satisfaction, commitment, even measuring motivation itself, right? And they give us a good sense of how our workforce is doing. But in and of itself, it's not that useful because just if we know the mean levels of those, what can we do with that? So what's particularly helpful is on top of looking at those key psychological outcomes or different types of behaviors like OCVs or performance, we also want to look at things that we think predict or are drivers of the outcomes. And this is where, when I had to do that exercise in class, I wanted you to think about these drivers from the standpoint of, well, what do we know from theory that we think are going to be drivers here? And so that's where you can turn to the research. You could also, in your particular setting, you could first conduct focus group research and talk to employees, and you might get some ideas there of people saying things like, I'm really unhappy and it's mostly because I hate my boss. So that could give you some insight into the local setting. And then you can also turn to external vendors. They do a lot of this with a lot of different companies, and they probably have recommendations on things that they've seen be important drivers in similar settings to yours. So those are all ways to come up with what you think would be the important predictors and what to include in the survey. And so, of course, all this is on the front end of really trying to figure out what to measure, because the results that you analyze are only as good as what you originally included in the survey. So the very first thing that you're going to do is clean the data. Typically, we would check for impossible responses. This really isn't too much of a concern these days with the use of Qualtrics, because the way that it's set up, you really can't have impossible values. But if you're doing paper and pencil surveys, that would be an issue. So the second thing you want to do is think about dummy coding your variables. So I'll show you what I mean by that. So I'm going to log into my account here, and you can see, so here's our survey. So what you can do within Qualtrics, and you'd want to do this on the front end before you get all your data when you're creating it. So if I right click a given question, I can see this recode values. So I can tell it that I want someone to answer strongly disagree. I want that to be coded as a 1, 2, 3, 4, 5. That's typically what we do for a Likert scale. And it does that by default if you do that response scale. And it'll do that the same thing if you do any kind of like 1 to 5, 1 to 7 response scale. It knows how to code those. Where it gets tricky, and this it would code the same way, like 1, 2, 3, 4, 5. Things like gender. So I can do recode values, and then I can say what I want it to assign, male and female. So now I know, and I can mark elsewhere or input it into my data file later as a reference that male is 1 and female is 2, and other would be 3. The one that I think that I usually change the most are yes/no things. I like for yes/nos to be 1 is yes and 0 is no, because that's inherently meaningful to me. Okay, so now when I export my data, and I export it when you export data from Qualtrics, you're just going to data and analysis, export data, and then you can pick what form you want it in. And then I usually do use numeric values because that's what I'm going to ultimately be analyzing, and then it will have 0 and 1 for those managerial values. And if I export it into SPSS, then it will automatically add those labels into the labels column, so I'll know 1 equals yes, 0 equals no, 1 equals male, 2 equals female, or whatever. If you do other formats, it doesn't have that same characteristic there. But of course, you can just have a separate code book that gives you that information. Okay, so that was just an example using our data set that you're going to use moving forward. With the data set here that we're using for this example, I've already gone through and done this. Then you need a reverse score as needed. So sometimes we've talked about we include reverse scored items, right, that kind of go the opposite way of the rest of the items in the scale. So we need to make sure we take care of those and appropriately recode those before we do any type of analyses on them. And then we can look at descriptives of variables as well as creating the composite variables. And in doing this, you want to check for the reliability. And you could also do some factor analysis. So I'm not going to, in this presentation, talk about factor analysis because I think it just goes a little bit beyond the scope of our class. I know you've talked about it elsewhere. And in reality, I think people don't quite do it probably as much in practice. So we'll just focus on the reliability aspect. And then at this point, you'd also, let's say you were trying to link this attitude engagement to some other file that you have archival data within the company. So one thing that's often done is linking these with performance ratings. So you're pulling that from the performance appraisal system. This is the point when you would want to merge those data files. And there's different functions you can use depending on how you're storing your data within Excel or within SPSS. But I'm not going to cover that either because that's just really going to depend on the format of the data that you are using. And most of what I know is in SPSS, and we're not going to actually do analysis in SPSS, so it's a little bit of a moot point. Although you can always work with your data in SPSS and then convert it to another format, which is often what I do, just because I'm most comfortable with SPSS. Okay, so originally this lecture was going to be all about how to do this in R, and I was speaking with a colleague, Scott Tony Dandel, whose work we're going to reference at the end of this, and he's big in IO in the statistics world, and he told me about this program called Jamovi. So what I want you to do right now is go ahead and download Jamovi. Here's the website. Should be a quick download. Once you do that, open up the program. Program looks like this. So what's really cool about Jamovi is that it has an interface that's much more user-friendly. It looks a lot more like SPSS than R does. It's not just syntax-based, but it has this function where you can click syntax mode, and then everything you do from this drop-down, it will go ahead and create the syntax for you that can be used in R. So what's nice about this is you can run your analysis in this, and then you could copy all that syntax and later just rerun it all within R. It's also really useful if, let's say I just don't know the code for something. I can use the drop down here, see the code real quick, and then I could input that, if I'm working from existing code within my RStudio or something. So I think this is really neat, something I just myself discovered. So let me get my screen a little bit off here. So what we're going to do next is I want you to pull the file data for survey tutorial in Jamovi from, you should download that from ELC, and then you're going to go to open here, browse. My computer has a weird delay. Come on. Okay, so this is it has to be saved as a CSV file to use in Jamovi. which is how it's saved in ELC. Open that, and voila, we see our data there. So I'm going to try to do this where I can get kind of both screens on here, but I'm not exactly working with me. So we'll come back here for a second, then we'll go back up there. Okay, so we pulled in the data. I showed you how to do that syntax mode. And then from here, we're going to have to do a few things to clean up the data set. So it automatically imports the data. You see these little images right here to the left of each variable. So again, this is just like SPSS. Each column is a variable, each row is a person. These are the people ID numbers. So these are all, if you right click a variable, it gives you info about it. And so for some reason it just automatically imported as nominal. These are actually continuous variables. So you just want to go through and change them. It's kind of a pain. There might be a way to get it to come in from Excel automatically being continuous, but unfortunately I am not aware of it. So I'll just quickly do this. Now there are some that actually are nominal in our data set here. So turnover, we can consider that a nominal variable because 0 is you didn't turn over, 1 is you did turn over. Country is nominal, coded as either US or China, and then level is supposed to represent job level. 3 different job levels there. So I will leave those as nominal. And then just as an aside, so this data that we're using here is 3-item scales measuring relationship with manager, career development opportunities, autonomy, injustice, engagement, job satisfaction, turnover, intentions with a single item, and then actual turnover. And so turnover, when I was talking about merging data files, that would probably be something that you would get from another data file that exists within the HR system of the company. Okay, so now the data is in good shape. So I can move on to my next step here, which is to reverse score as needed. So in this case, only one of our items were reverse scored, and that was Injustice 3. And so what I'm going to do is recode that variable. And there's a couple ways you can do this, so I'm just showing the way that I usually do it. So what you're going to do is go back over here to Data, Compute. Now scroll. This is where this program's a little bit funky. So you really, before I press data, I'm going to delete this variable because it just randomly created something. I want to be on this very last column here and then do compute variable. Now, I'm going to type in Injustice 3R. That's what I like to do with reverse coded variables. I like to not just overwrite them in my data set. I like to have a separate variable just so I can, if you overwrite them, sometimes you get confused. Like, wait a second, is this the original score? Is this the reverse scored? And then you kind of have to go back to the raw data and it just gets to be a nightmare. So I like to have Injust 3 stay in the data set and then Injust 3R, which I'll eventually work with. So it's a 5-point scale, so I can do this function. So this is telling it compute a variable called Injustice 3R. That variable is going to be 6 minus people's current score on Injustice 3. And that's just a way you can reverse score easily a 5-point item, right? So if they scored a 5 on it, 6 minus 5, it should be flipped to a 1. If they scored a 4, it should be flipped to a 2, and this will solve that. So once I'm done with my function, I just press enter, and you can see down here, now it's computed that for me. So if we compare Injust 3, 3, 2, 1 were the top 3 people. 3 stayed the same. 2 should have been a 4. 5 should have been a 1, so that's right. So in this case, that's the only reverse score variable that I have. So I'm settled there. Now I want to just do a little bit of screening of my variables. So here in this step, I can calculate reliability as well as get the descriptive statistics for the various scales. And there's a couple ways to get descriptive statistics for the scales. So what I'm going to do here, now I'm going to go to Analyses and Factor and click Reliability Analyses. And notice here, this is where you could do a factor analysis if you so wanted. But like I said, we're not going to get into that. I'm going to move this over just so we can see more. Okay, so now let's start with our first scale, which is Relationship with Manager. So I'm going to move those 3 items over, and I can check different things down here depending on what I want. Cronbach alpha is the typical internal consistency reliability. I'm also going to add mean and standard deviation. Now, the syntax mode, I never checked that. So add that on. Now look, see when I did that? This is telling me this is the R code you would use. So I could be outside of Jamovi, and if I put in this data set that I'm working with and put that code into R, I would get the same information. And it's pretty cool because it adjusts it right as you're going. So if I said I want to take away mean, you can see where that line goes away. So this is really cool, just also to help you learn the code and what the code means. So what I have here is it's telling me the mean scale score. So it goes ahead and creates a composite averaging those items. We're going to create our own composites later because this doesn't save that variable in any way. We're going to need to use them for additional analyses. But it's a quick and dirty way to get the scale mean, which is 2.24 across the 3 items, and standard deviation. And then I also can see my reliability there is acceptable at 0.863. So then I could do that for my next career development opportunities. You see, same thing. Tells me mean, standard deviation, good reliability there too. Now, this is where with the injustice, you just have to make sure you use injustice 1, 2, and then you're using that 3R, because that's when we're going to be working with from here forward. And decent reliability there. See, watch if I had used injustice 3, you're going to see that it's going to have a really bad Cronbach's alpha because that item is reverse coded, so it's not hanging well at all with the others. So I could do that for all of my variables, you know, and often we want to put those in some kind of like pretty table. So just showing you what I just showed you. Something like this. So when you're reporting, one of the key things you want to report about employee attitude survey would be the mean scores on those various scales. Now, here I also have some other information. If let's say you had done the same survey last year, you might want to include change from last year column. You know, we don't have that, so I just made that up. Or let's say you have some benchmark data, you know, from another organization or a consulting firm gives you that, then you could include that here too. So that gives a little bit of reference just for the company to know, kind of norming how are we doing relative to others. Another thing you can present is percent agreeables. So that makes more sense at the item level, because at the scale level you can't really get that in the same way because somebody could have responded differently to all 3 items. But you can break it down by item level and you could come up with a chart that kind of looked like this. So if it's a single item, you could easily do this, but with a multi-item scale, you'd have to show the percent by each category of response option. And then often you present the percent favorables, which would be the number that indicated agree or strongly agree. So I'll show you how you get that. You go to data, analyses, exploration, descriptives. And we'll do this career development opportunity variable again. And that shows me the overall mean of the individual items, but that's not really that helpful in terms of what I want. And then I click this, which should give me a frequency table, but notice nothing's happening. And then you see these pictures beside it. That's because it will only give you frequency tables for data that's considered nominal or ordinal. This is just kind of like a weird quirk of this system. Technically that's right, but the way we treat Likert scale, that doesn't make as much sense. So what we'll do is we'll go back here to data, and just temporarily, just to run this analysis, I'm gonna change these back to nominal. Also do that single item turnover intent. Okay. Now I'll go back to analyses, exploration, descriptives. Now I put those variables over, as well as turnover intent. Now when I click frequency tables, so for the first item, it's telling me the percentage of people that endorsed levels 1, 2, 3, or 4, or 5, corresponding with strongly disagree, strongly agree for all the items. And that's just exactly what I transposed right here. One thing I didn't mention here with basic data reporting that's on the slide is you could also add the standard deviation, but only do that if you think it's going to be useful. You have an audience that you think is going to understand it, because that can get a little bit tricky for people to really get a good grasp on. So know your audience for that one. Okay, so this just walks you through the different things that I've said. Okay, now we need to create those composite variables. So here we're going to go to data. Actually, first thing, we want to scroll over and just highlight this last row. And then I'm going to go, or last column, I'm going to go to compute variable. So I want to manually make the scales of the different variables that I'm using, that I measured, the different constructs. So let's start with, I think we have relationship with manager. And I usually just put _average. That's how I label my composite variables. You can call it whatever you want. And then here is, so essentially what I'm saying is like compute a variable, name it this, and here's the function. This is how you calculate this variable. I want it to be the mean, and this is case sensitive, so you have to do mean in all caps. The mean of relationship manager 1, relationship manager 2, and relationship with manager 3. And then I just press enter, and notice that it fills in down here. Now this shows you, if you click this shows you all the different functions that you could do. And you can do just, basic like I did before, subtraction, really anything flies. All right, now I'm going to click here again, new computed variable. So what else do I have in this data set? I have career development opportunities. And enter. We'll see that fill in. Okay, I think I have autonomy here. So this part is a little bit tedious, and this is where, if you were using code, you could do this a little bit faster with copy pasting. And then I'm missing one couple, okay, injustice. And do make sure, I know it seems tedious that I'm clicking this last column every time and then saying new, but if you don't do that, it doesn't always save them, and it just acts really funky. Remember, I have that reverse coded here, so I got to include that one instead of the regular 3. Now I've got my outcome variables, so job satisfaction. All right, and now I have all those composites computed. Keep in mind, it's case sensitive, so you got to put this variable exactly how it's spelled within your data set. Okay, so now I can get to testing some research questions, and here's where knowledge of statistics gets particularly important. So let's say we have some questions about difference between groups and how they score on our outcome or dependent variables. Like, let's say we're interested in, does one group of employees score significantly higher or lower on job satisfaction than another group? So if you think back to your statistics, this is anytime we're trying to compare mean differences between groups or a variable that has 2 levels, independent variable having 2 levels, that's when we use a t-test. And in this case, this is the independent sample t-test because the 2 groups are different people. So we're going to use the example of, do employees in China versus the US have different jobs, significantly different job satisfaction scores? So it's independent samples because the 2 samples are completely independent of each other. They're not the same people in each sample. And we'll come back to some of these other ideas in a second. So to test that question, what we're going to do is we're going to go to Analyses, t-tests, independent samples t-test, very straightforward. Then we're going to put our dependent variable in. So I said we are interested in the question of job satisfaction. And then our grouping variable, this is going to have to be a nominal variable. So here it's country. And if I scroll down, it gives me some different options of things I can choose. So I'm actually going to leave them all as they are checked. This is just different ways of calculating. Looks like. Okay, so that it did just freeze on me, so do make sure that you're periodically doing file save, and you can actually save this as a Jamovi file, and then when you pull it back up, you can just leave off right where you started, or where you left off. So job satisfaction is the dependent variable, because that's what I want to know. If there's group differences on. My grouping variable again is country. And like I was saying, the different things here, that's a little bit more nuanced than we'll get into. So I'm just going to leave the standard there. If you want to get effect sizes, you could do that. I will check descriptives because that will tell me some mean information. Okay. And then my hypothesis, if I have a directional hypothesis, I could click this and that would do a different tailed significance testing, but typically we're going to do the two-tailed testing, which would be this first hypothesis. So now I look over here, and here's my output. And I have some interpretation of it for you over here. Okay, so what it's telling us is, this is the t statistic, okay? So t is equal to negative 2.57. That's the degrees of freedom. If you remember from t-tests, whether or not a t-value is significant depends on the degrees of freedom. And at this particular degrees of freedom, the associated significance value or probability value is 0.01. So that is less than that cutoff we usually use of 0.05. And remember, we consider something statistically significant if the p-value is less than 0.05. Meaning there's a less than 5% chance that that would occur by chance. And So we can reject our null hypothesis. Said otherwise, if all that seems like statistics gibberish to you, just think of it this way. You want that p-value to be less than 0.05. If it's less than 0.05, that's telling you there are significant differences between the groups. So if it's significant, it's less than 0.05, the groups meaningfully differ. So we can say there are statistically significant differences in job satisfaction between people in the US and in China. Now we look down here to this descriptives. That shows us for each group. China was coded 2, US was coded 1. The means, so we know that the Chinese employees have a significantly higher mean, so they are more satisfied overall. If this t-statistic was lower and this p-value was greater than 0.05, we would conclude there's no meaningful or significant group differences. So that's when you just have two levels or two groups of the independent variable. Let's say you have the same question. You want to know, are there differences in job satisfaction, but you're dealing with a variable that has more than two levels. So let's say 3 levels. So let's say we want to know, do employees at different levels within the organization have significantly different job satisfaction? So this is where we would use a one-way ANOVA, and we would have to do post hoc tests to tell the nature of these differences. So I'll explain that in more detail now. Okay. So here's our basic question. Move back over to so you're going to do ANOVA, one-way ANOVA. Dependent variable here is still job satisfaction. So I find that job satisfaction average variable. And then the grouping variable now is level. So this was coded 1 if you're entry level, 2 if you're middle manager, 3 if you're an upper level manager. And notice it has those two images there, meaning this variable has to be nominal or ordinal, and it is. Again, some stuff to check here. So I would leave it on don't assume that the groups have equal variances. They're just slightly different adjustments that are done. You could click descriptive tables. I'm not going to for now. Post hoc tests. So this really only matters if your overall test is significant, but I'm going to go ahead just for our purposes, and I usually use Tukey, but you could use the other one as well, GamesHow. And then I'm going to say flag significant comparisons. Okay. And you can see my output here. So I'm going to walk back over to the PowerPoint slides that walk you through that. And I just realized I did not add information here about the steps, so I'm going to really quickly, you're going to go to Analyses, ANOVA, to get to this. Okay. So that's what we just did, and here's the output. Okay, so the first thing you're looking at, the first thing that comes in the output is telling you the overall F value. This is saying overall there's some differences somewhere between these 3 levels, these 3 different groups, and in job satisfaction. F value is 0.143. That corresponds with a significance or p-value of 0.867. That is greater. That's a lot greater than 0.05. So that is not significant. So what this is telling us is there is an overall, or we call it an omnibus test of there are no group differences in job satisfaction based on grouping people by their job level. Okay. And that's where we would stop here. Now let's say for just illustration's sake that we did have an F value that was large and our p-value was less than 0.05. So our overall test that there are some significant differences somewhere. That's where you would run these post hoc tests. So again, here they're not going to be meaningful because we didn't find a significant difference, but just to interpret these, if you do get a significant F value. What this is showing is the comparison between group 1 and group 2, and that's again whatever you labeled it, and this shows how I labeled it in this data set. That's the mean difference, and that's the p-value associated with that mean difference. So we want these p-values to be 0.05 to be able to say two particular groups are significantly different. So if this one, group 1 and 2 here, it's 0.896, but if it was 0.006, then I would say group 1 and 2 are meaningfully different. But then it might be that group 1 and 3 are not. So it's just identifying where the sources of the differences are. And when I click the flag significant comparisons, it'll put an asterisk. See how it says note there for those that are significantly different. So it's easy for you to eyeball it and tell. Here none were, so that's why you don't see any asterisks actually showing up in the table. And then another thing you might want to do if you have differences between groups, you might want to see, when we do a driver's analysis, we'll get to in a second, does that differ between groups? Are there different drivers of engagement for upper managers versus entry-level people? And we're going to come back to that question. All right, so now moving on to what I think is probably the most interesting analysis is key driver analysis, fancy name to just say doing some kind of regression. So often we want to know what are the key predictors of our outcomes of interest. So what is causing people's job satisfaction to be higher or lower? And I'm using the term causing loosely because we know here we don't have causal data, but we tend to kind of present it that way, particularly when we're talking to people in an organization without too much of a background in this type of thing. I think we do want to give the caveat that we can't firmly say this, it's all based on correlational data, but it's sort of set up to think about it in causal terms and talk about it that way. So, what we can tell from regression, I hope this is a little bit of a refresher for you, is that, how much variance in the outcome can be accounted for by the predictors. So that's kind of a fancy way of saying, if we know where somebody stands on some predictive variable, like if we know how much autonomy they have, how well does that help us predict how engaged they're likely to be in the organization? And R squared is the metric that tells us that. You can also look at different constructs together and see which ones predict incrementally, meaning like some things overlap a lot. If we measured something like maybe autonomy and feedback, perhaps those, I'm just throwing out ideas, correlate super highly, then we can see how each one uniquely predicts above the other. If they're too highly correlated, they're really redundant, so there's no use looking really at both of them. But there are some drawbacks to multiple regression. A lot of times our predictors are really highly correlated, and that can cause some issues with what's called multicollinearity, which can make it hard to really know how to interpret results. Also, I find that beta weights, which is the coefficient that a regression analysis gives you, are not that intuitive, meaning like you see that number, you don't know what that number means. So I'm going to show you how to do regression, but I also think the probably better way is to use an extension of regression, which is called relative weights analysis. And what this does is it takes into account the issue of super highly correlated predictors. So it allows you to essentially, I won't get into the math behind it, but it does a lot of different variations of looking at combinations of things, and it kind of lets you rank order all the predictors in terms of the percent variance explained in the outcome, taking into account their correlations with each other. And you can look at significant differences between the weights, which by weights there I mean significant differences between the percentages of variance accounted for. So I think that'll make more sense when we go through it, but that's just kind of an overview of the next two things I'll talk about here. So I always like to start before I do a regression with a correlation. And the reason is regression is an extension of correlation, and I think you can just see a lot from your data with correlation analysis. So I'm actually going to do a save, haven't saved in a while. Analyses, regression, correlation. And I like to put things in a particular order. So I like to put the outcomes at the either top or the bottom of the correlation matrix together. So I'll put the predictors first, then the outcomes, and I'm going to also include turnover intent and turnover here. Now we could put country in because it's a dichotomous variable. Level is not going to be meaningful here because it's coded 1. Well, it might be kind of meaningful because it's coded 1, 2, 3 with 1 being the lowest level, 3 being the highest level. But be careful when you're dealing with categorical variables. If they're totally randomly coded, like race, for instance, you would have like 1 through 8 for different racial or ethnic identities, and that's not going to make sense in a correlational context because there's no like inherent higher value of whatever race you coded 8 compared to whichever race you coded 2. But we don't have anything quite like that in the data, but I'm going to leave level out regardless. All right, so for our purposes, we're just going to keep it at Pearson. There are some subtle differences here, but I'm not going to get into them. And we want to flag significant correlations. Here's our code. And then it gives us a pretty correlation matrix. So I'll go back over here. We're going to spit it out. So now you can see the top value is the R, or the actual size of the correlation, and the p-value tells you if it's significant or not. Again, it's also going to add those asterisks there, so it's an easy way to eyeball what's significant. And here we have a lot that's significant, so I like to just kind of look at this job satisfaction column so I can see, wow, those are some fairly sizable correlations. All of our predictors seeming to matter there. Same with engagement. Not everything's mattering for turnover intent, and look, when you get to actual turnover, the only thing that's significantly correlated with it is turnover intent, as we would probably expect, but that's still even low. And that's not too surprising, right? Because there's a lot of reasons why people actually do or do not leave the organization even if they're dissatisfied. And I could have put demographic information in here too. Actually, this output doesn't show. I didn't put the country variable in, but here trying to get this to show you a little bit better here, but so this is showing you country's correlation with all the different variables. None of them are significant. And this is really better tested via a t-test, but sometimes it's like, can give you a little bit of insight depending on the nature of the variable. Like if it's gender, you're going to get similar information here. If you get a significant correlation between gender and job satisfaction, when you run the t-test, you would also find significant differences. So it's all based on the same underlying ideas, just different ways of looking at it. So now we're ready for regression. So what I might do is, if I had tons and tons of variables, if something's not significant in a correlation matrix, it's not going to be a significant predictor within the regression analysis. So if I have tons of stuff, just to keep it simple, like let's say one of our variables here didn't correlate with job satisfaction, I might decide not even to look at that further. And this is where you got to think about, what you want to do exploratorily versus what you go in kind of with hypotheses and ideas about, depending on your particular purpose. All right, so now I'm going to run a regression. If I'm doing a continuous outcome, I am doing a linear regression. And most of our outcomes are continuous. So let's see, keep working with job satisfaction as our outcome. And with this analysis, you can only do one outcome at a time. There's other things you can do with more than one, but I'll show you that with the relative weights analysis. So this is a little confusing because it calls continuous variables covariates. That's not 100% right in terms of statistically, but don't worry about that. It's doing the same thing statistically, it's just kind of a strange label. I'm going to put all 4 of my predictors in there. And if factors would be the nominal variable, so I could also add in country there or something. So got my syntax, got my outcome, and I want to also add a few things here. So I do want to do an overall f-test. And it's already got the r-squared clicked. You can do, it gets into, You can do some other different types of tests here, and for our purposes, I'm not going to get into those too much. So let's interpret this output. Okay, so first I look at the overall model test. So this is the F value of the overall model. This is the associated p-value. It's less than 0.05, so that means this overall F test is statistically significant. If it's not, then you probably don't really want to pay attention to it. It's going to be rare, though, when you have multiple predictors, that the overall model won't be significant. This also tells you the R squared. Remember, R squared means percent of variance accounted for. So what we can conclude from this is in our set of predictors here, our 4 predictors, account for 40.6% of the variance in job satisfaction. So if we know where somebody stands on relationship with manager, autonomy, injustice perceptions, and career development opportunities, we can predict with about 40.6% accuracy where they would stand on job satisfaction. It's another way of thinking of that. Then I can look here and see, well, which of these predictors were significant. The overall model is significant, but that doesn't mean each one's going to be. And indeed, that's the case here. So only, here I'm again looking at that p-value column. So it's taking this is the estimate, is the beta weight. So it's taking that beta weight, conducting a t-test on it, using that to calculate the significance value. The main thing you need to know, though, is you want to see things that are less than 0.05. So that means if it's less than 0.05, we can conclude that that beta weight is significantly different than 0. So here we only see that with a relationship with manager and career development opportunities. So those are the only 2 statistically significant predictors of this group. And here's another way, like if you wanted to depict it for somebody, kind of showing, like I said, those causal arrows. Again, it's not really causal, it's correlational, but for illustration's sake, this helps. So I use the asterisk to show it's significant. These 2 aren't. So that's where it can get a little bit confusing if you're presenting this to someone not familiar with statistics. You might decide that you're going to you would just leave out these numbers because technically we're saying they're not different than 0, but somebody's going to see them and not interpret them that way. So I might even just not put numbers here and say, we tested these, but they're not significant drivers. The 2 that are standing out are these. And then just to give you another way to think about how to interpret the betas, which I said again are not so intuitive, but what this 0.27 is telling us is that a 1 z-score increase in career development opportunities, and I say a z-score increase because things are always on the same scale, and betas are standardized. In career development opportunities, a 1 z-score increase in that would result in a 2.27 z-score increase in somebody's job satisfaction. So I think that's kind of a powerful way to talk about stuff. So you could actually convert that into some numbers, right? So somebody has you could say if they have a score of this on career development opportunities, then it's going to, and it goes up by 1 point next year, then their job satisfaction will subsequently move from 3 to 3.27. So there's things you can do to plug those in and give actual numbers, which are sometimes more tangible for people to interpret too. And I'm not going to ask you to do that in an assignment or anything. This is just, I think sometimes it's useful to think about what the numbers mean in a little bit of different ways. All right, so now that brings us to our last analysis, which is your outcome is dichotomous. So our example in our data is turnover. So you're going to go to analyses, regression, 2 outcomes. So you can use this when there's 3 levels or more. You can do a multinomial. It gets really complicated to interpret, so we're just going to focus on binomial, which most of the stuff we do falls into. So I'm going to put turnover. Again, notice it's going to require it to be a nominal variable. Again, I'm going to put my 4 predictors in, and I could put other things in here as factors, other nominal variables if I wanted. And then I just want to click, I want to get the odds ratios, and I want to do an overall model test. And I get this output with that associated syntax. So this is telling us our overall model fit. So it's the analog to the F test we did before. a couple different fit statistics show up here, but the chi-square is kind of the main one here and is not significant. So this overall model is not even significant. So I really wouldn't look at it further. For illustration's sake, I will though. So go down here. Again, we're looking for p-values less than 0.05. The intercept significant, we don't care about that. All the rest are greater than 0.05, so none of the individual variables are significant predictors of whether or not somebody turns over. And the way you interpret odd ratios is if it's greater than 1, that means there's a greater likelihood. So like more autonomy would mean greater likelihood of turnover. Again, it's not significant here, so that's not what it means, but for illustration's sake. And then less than 1 means inversely related, so good relationship with manager would relate to less turnover if that were significant, assuming actually turning over is coded 1 and not turning over is coded 0. Before we move on, we're going to exit out of Jamovi, but I do want to show you, so what this is keeping is a record here of everything that we've done. It doesn't record, unfortunately, when you compute the variables, which is a little bit of a bummer, because it's nice to have that information saved. But that's something that I think you could record elsewhere. But I can right click. Sorry, if it will let you right click, you can right click on syntax and copy it. And then I could copy the syntax all into a separate file. I could save that syntax alone. I could save the whole thing. I can save this whole output file. So anybody else could come in and see exactly the code I used to get to where I got. And that's really important in terms of tracking exactly what you did so that other people could replicate it. And again, I would recommend that you do that. If you're going to use this program for the computation stuff, I would recommend that you have some way that you do trace that, like maybe you copy paste those formulas into another document so that somebody understands exactly what they mean. So that's one drawback of this method, where if you're using just straight up R, you would definitely have a record of that. But to me, this is so much more user-friendly and captures almost all the things that you're going to need to be doing at kind of the basic level of statistics. And even a little bit beyond that I think the trials with using R are not quite worth the small trade-off here that you're getting by not getting the full amount of syntax. So I highly recommend Jamovi, completely free, and interfaces with R. And you will notice, I do want to say one last thing about it, that if you look back at your notes from some of your other courses, you're probably going to see different commands used for t-test. And that's because there's different ways to do the same thing. And I'm guessing when you were taught this, you used the psych package within R, which just simplifies the commands. So if this doesn't look like what you had in your previous courses, that doesn't mean it's wrong. It's just two different ways of getting the same thing. And if you ran it those two ways, you would get identical results, save for some rounding error. Okay, so now I want to move on, and we're going to move out of this program and talk about how to do relative weights analysis. So to do this, we're going to go to this website. This is a website that my good friend Scott put together. First thing you have to do is decide what type of analysis you're going to do. So if you have a continuous outcome, actually I'll come back to this. Here's the choices. If you have a continuous outcome variable, like job satisfaction or engagement, you want to use the multiple regression one. If you want to look at multiple outcomes at the same time, then you can use multivariate. I'll explain that more in a minute. And then again, if you have just a dichotomous outcome, like we just showed with turnover, that's where you'd use a logistic regression one. So we'll start with multiple regression. So the first thing that you have to do is download or upload your file. So you could download code and then run this in R yourself, or you can have it sent to an R server and then it emails you the results. That's what I usually just do. So you choose the file, and here's where you're going to want to go into ELC, and you'll see a file that says for RWA analyses. That's the one you're going to want to use here. And this has to be a CSV file. So I'm going to put my email in. Then the data we're using is raw data. You could do pair or listwise deletion. We don't have any missing data in this data set, so it doesn't matter. And then name of the criterion variable. Criterion is another word for outcome. So you have to put this exactly how it appears in the data set. Just job set av. And then list out your predictor variables. So we have relationship with manager, average, autonomy, average, career development, average. I believe that's how it's labeled in this data set. And let me actually just double check that I used the labels that were the same as what I saved here. Yeah. Okay. For now, we're going to just leave all this stuff alone. And then I'm going to press submit. And then I'm going to be patient. So I press OK, and then I'm going to wait a few minutes till this shows up in my email. I'm going to pause this, and I'll open up my email when it does show up. Okay, so the R output arrives to me like this. It comes from Apache. It's like a bunch of gibberish. You just want to scroll all the way down to the bottom. And from here down is what we care about. And I have already included that in this next slide. Okay. So I'm going to walk you through how to interpret this. So the first thing is it's telling us the R squared for the model is rounding up 0.41. So we're accounting for about 41% of the variance in job satisfaction with our 4 variables here. That's very similar to that's the same idea we found before with the regression rate. Now, we get 2 different things here. We get the raw relative weights and the rescaled relative weights. So with the raw relative weights, this is the blue, corresponds down here, R, is these tell us just the amount of variance in job satisfaction accounted for by each of these variables. So these will sum to the R squared value. Okay. I just took these numbers directly from there and convert them to percentages. And these tell us, this red tells us the confidence intervals around those raw relative weights. So confidence intervals, it's essentially just another way of talking about p-values. So it's like how sure we are, the kind of the band of where that effect size could fall. And we don't want them to include 0. If they include 0, then we'd say it's not significantly different than 0. I told you that right. Oops, right there. So what we see here is relationship with manager goes from 14% to 32%. That's significant. No 0 included. Career development opportunities goes from 8 to 22. That's significant. The look autonomy starts below 0, includes 0 in between those 2 numbers. So it's not significant. Same with injustice perception. So just like parallel to what we found with the regression analyses, those are not significant predictors. So I might actually just leave them off or just put a dash when talking about them. Here you can actually, it's a little more intuitive because this is telling you again, of the variance of what we can predict somebody standing on job satisfaction with 2.1% accuracy if we know their autonomy score. But because it's not significant, we would, we would say it's equal to 0. So again, I might just not go there with those. It's your call depending on your audience. But these two, fairly good predictors. So if I know someone's standing on the relationship with their manager, I can predict 22% accuracy or predict 22% of the variance in their job satisfaction. Puts a little more raw, concrete numbers to things. Now, the rescaled weight, I think this is pretty interesting too. So this is saying, so of that 41% of variance in job satisfaction we can account for, where do each of these variables fall? So these are always going to add up to 100% because it's 100% of that 41%. So we can account for one slice of the pie. Well, of that slice of the pie we can account for, what percentage is attributable to these different variables. So the numbers are always going to be higher than the ones below, assuming your R-squared is not 100%, which it never would be. So you could kind of illustrate this even with the pie image, putting a slice of the pie that equals that 41% and then showing how these each factor into that slice of the pie. So the rescaled weight there, you don't have to convert that. It's already in percentage form. Same idea. I just transferred those values over. So relationship with managers, 56%, career development, 36.49, autonomy 5, injustice perceptions, 2.13. It doesn't give you significant values for those. So it's up to you, depending on what you want to present. Just two different kind of ways of looking at the same idea. Now I mentioned earlier when we got group differences. You can also do a subgroup analysis. So let's go back to our website. Oops. Okay. Dun-dun-dun. Alright, so here's what's different from what we did before is a grouping variable. I can test for statistical significance between two groups. Let's say the grouping variable here, we want to do that country analyses. And I have to tell it what the values are, so they were coded 1 and 2. And I submit, and again I wait. Now we won't wait, just for time's sake. But here's what I promised you would get in the email. So now it does all the same stuff that we just talked about, but for group 1, and I have to know how it's coded. So here, US is 1, China's 2. So here's all the results for the US, so I can write those out, this blue corresponding to the blue down here. All the results for group 2, which is China. Same exact process I was using before. One drawback here is in terms of the R-squared, it only gives you the overall R-squared, which would be the same as the one we ran before, that 0.405. It doesn't tell you the R-squared for each country separately. So in that sense, you don't know, it's just estimating this, I guess, on the overall 40.5 rather than for each group separately, the rescaled weights. But the interpretation is essentially the same as it was before. Now it's just breaking it down by group. And what you could do if you did want an R-squared for the subgroups separately, you can split your data file up and run it on just each half of it. That would be kind of a workaround. But what it does do is it tells you a comparison between the two groups. So here, the confidence interval, this is the comparison, meaning for a given predictor, are those values significantly different across the two groups? So like, is 10.7 significantly different than 20.8? If we look here, all of these include 0, actually. So in no case are these significantly different, even though they kind of look like they are, right, if you just eyeball it. So, here is where, when you're presenting this, you don't want to, you would probably not want to present this because somebody who doesn't know about statistics, might eyeball this and say, oh, China, career development is so much more important in China, when actually from a statistical standpoint, they aren't different, or at least we can't say they're different than what we might find by China. Then this brings us to multivariate relative weights analysis, and this is a pretty cool extension, I think, that's unique here and that you couldn't do with what I showed you in Jamovi. So I'm not going to go through the same process here if you had clicked on multivariate RWA. The only difference now is it lets you put several criterion or outcome variables. And so I put job satisfaction, engagement, and turnover intention. That's mislabeled in this, it should say turn intent. And my same predictors. And when I ran that and sent it to my email, here's what I got. So essentially, it's the same exact interpretation as just the regular RWA in terms of how you apply the numbers. But what's different here is it's taking this, it's the equivalent of a MANOVA, if you learned about that. It's taking it's like a composite variable where it's kind of combining all of these outcomes. So you might want to call this like a morale factor. Like all the good stuff. On average, how much of the predictor is predicting the good stuff? And it's taking some kind of linear combination of those outcomes to come up with this. This is nice if you just want like one solid number to present to people, rather than here's the results for job satisfaction, here's the result for engagement, here's the result for turnover intentions. So what you can see here is the R squared goes down, and that's largely, I think, because we're not as good as predicting turnover intentions. It typically is going to go down because it's harder to predict a lot of variance across 3 different outcomes. But then we can do the same thing here. So got the data pulled for what we can tell here is, we're on average predicting 7.9%, that would be the highest of the variance in, I'm going to call this morale factor, based on knowing somebody's quality of relationship with their manager, and that's significantly different from 0. And in this case, autonomy popped is significantly different, but injustice did not. And then same thing, the green here is representing those rescaled weights. So the conclusions I'm drawing throughout just the regular RWA and the regression are quite similar. It's just statistically taking multicollinearity into account a bit more and giving you numbers that I think are more intuitive for people to work with. And then here it's allowing you to have a, like I said, just kind of give you one grand overall number. So here I might look at this and say, okay, well, what am I going to work on? Well, relationship with manager seems to matter the most, so maybe we want to focus on that. And I'll talk a little bit more on that in a second. Finally, the logistic one. So here, same thing, just if you have turnover as the outcome. And exact same interpretation. Now look at the R squared here, 0.3%. I would say in reality, if you have an R squared that small, you're probably not going to say anything. We already saw with the regression analyses, same thing. Like we're not doing a good job predicting turnover with the variables we measured, so it's really not worth talking about it other than just to say that we weren't able to predict turnover from X, Y, and Z. Okay, so the last thing I want to talk about is applying this knowledge. So from a practical standpoint, what do you do? What kind of recommendations would you make? And here you can use what's called the heat map method. So a heat map what it's doing is you're using a scatter plot that takes into account the size of the relationship between predictors and outcomes. So like you could do this with beta weights or regression, or relative weights, those percentages. I'm going to use relative weights because I think they're more intuitive. So which ones are the strongest predictors, but also how are we doing on those currently? And you can divide this into 4 quadrants. So essentially, if something has a high impact, matters a lot for predicting, let's just say job satisfaction, and we're doing really well on it right now, like people were scoring very high on autonomy and it matters a lot, then that's something we want to keep promoting within our organization. That's when you get to this top quadrant here. On the other hand, if something matters a lot and we're not doing well on it, so we score low on it and it's a big predictor, that's a key focus area, right? So we're low performing, it's a key driver. Really, that's where we should focus a lot of our efforts. And then you have things that aren't as good of our strongest predictors. If we're doing well on it, we just want to kind of think about maintaining it. If we're not doing well on it, but it's not a super strong predictor, you want to keep an eye on it because you're not doing well on it. But you don't need to focus on the same way because it's not mattering as much. So here's a plot with our data. So what I did was, if you do insert chart, I did a scatter plot, and I plotted the, this is giving us totally different values here, but essentially I plotted on the x-axis, I plotted the relative weights, so I put the relative weights there, and on the y-axis I plotted the means. So I'm going to close that out just for confusion, but if you want to do this on your own, that's how you would do it. So, get rid of this. Okay. So this again is a focus quadrant, and 2 of our things ended up there because they were strong predictors and we weren't doing well in them. So what does it mean not to be doing well in them? So where do you draw the lines in these quadrants? And this is a judgment call. So you could take the mean from within your data, right? So like of all of our predictors, I could calculate the mean of where we scored on all 4 of these, and I could make that the cutoff for low versus high mean, the mean of the means. Alternatively, I could use, and that's what I did here, was the mean of like the midpoint of the scales, which is a 3. So saying that we're doing average on that, because that's what that number kind of represents inherently, that's going to be a judgment call for you. Same thing here with the relative weights. I could come up with some arbitrary number that I think is a meaningful, strong predictor. There's no like clear number that represents that, or I could look at it within my data and think about what the average kind of number is. So here I'm plotting these were the raw weights, so the ones that, not out of just our piece of the pie, but overall what percentage of variance are we counting for. And then I just got the means straight from, this is what I pulled from SPSS because I had the data in that originally. But we got those means when we did it in the Jamovi program as well. Same things. And so I would probably make the recommendations then that we should focus on career development and relationship with manager. So I might even say, okay, here's our prioritization plan. I might list them in order 1 and 2. I picked relationship with manager first because that's the one that's the strongest predictor, and they're very similar in terms of how low they are. And then I might say with autonomy and injustice, those aren't biggest predictors, but we want to be careful because injustice is lower than we'd like, but it's not as big of a priority as the other 2 that fall in that focus quadrant. You also have to think about priority plan in terms of some practical things, right? Like, depending on what you measure, you should always try to measure predictors that are going to be actionable in some way. But if you have something in there that's not super actionable, then it doesn't really make sense to talk about prioritization. But here, like relationship with managers, that's something that you can think of a lot of different interventions that might help, as well as career development opportunities. So these feel like very tangible recommendations that we would say, if we can increase these, we can go a long way in terms of promoting employee job satisfaction. Okay, so that's it. So just make sure that you do download Jamovi on your computer, the laptop that you're planning on bringing to class, because we don't want to waste time trying to get that up and running, and that you have the data files for the new data that we're collecting. I'll send those out to you, and those will be on ELC, but you just want to make sure you have access to those, because that's what we will do the assignment next time we meet based on that other data set. But it will be very similar to the concepts that you learned here. And I will be walking around helping you answer any questions that you might have. Thanks.